on the east coast of Australia. And then I think there's probably about 2 years for the rest of the country to adopt to the standard set out by Safe Work Australia. Then we'll run quickly through the engineering controls and look at the effectiveness of these controls. And then finally, probably one of my favorite topics right at the end is the critical component in the overall engineering control space. And this is how we deal with vacuum cleaners, which ones to select and how to maintain them. So what are we dealing with? Well, silica really as an element comprises nearly 60% of the Earth's crust, and in its crystalline form, it's really hard. And crystalline silica is effectively it's quartz. Quartz in German means hard, and that's exactly what it is. It's just a very hard crystalline particle. And here's some scanning electron micrographs of crystalline silica particles found in Sydney sandstone, where my mouse is hovering. And then we look at them when they're in aggregate form in concrete. Now, really what happens when you disturb these particles, they just stay angular. They get smaller as they get broken down their cleavage planes. They stay angular and they just get smaller. It's really as simple as that, but it's really interesting to see what they look like physically. Now, you can imagine what happens when these particles get into your lungs. Your lungs just really, in the respirable range, your lungs don't want these particles in them, and your lungs struggle to dissolve them. So when your lungs start to try and dissolve them, they get surrounded by small particles called macrophages. And when the macrophages decide or discover they can't dissolve these particles, they die. And they release an enzyme which scars the lung tissue. And the accumulation of that scar tissue results in the lung stiffening over time. And that eventual condition is known as silicosis, which has a range of severities depending on time of exposure and the sheer concentration of particles that you breathe in. But it's also being linked as time goes by to more and more autoimmune diseases. And it's also quite closely linked to obstructive pulmonary disease. So it's not a good thing to encounter, and it's an important occupational health topic to tackle, particularly as we experience a workforce that stays longer in construction, and particularly as we increase retirement age. So because it's everywhere in the Earth's crust, you find it in all materials in construction in varying percentages. Clearly, the worst candidate is in engineered stone, but in concrete, which is really what the form that we're in today, you can get anywhere between 5 and 40% of the material can consist of crystalline silica. And it gets liberated, or workers get exposed to it in 2 ways. Firstly, when you disturb it through cutting, grinding, or drilling or breaking concrete. And then if you haven't controlled that dust at source, it settles, and then it can be redisturbed when you try and clean up or when you drive over it and walk over it. So you can be exposed on 2 occasions. Another consideration, particularly in the remedial space, when there is a lot of cutting and there is a lot of grinding, is the question of aerodynamics. These particles, when they're in the respirable range, less than 4 micron in diameter, they take a long time to settle. So a 1 micron particle can take several hours to sink just 1 meter, which is quite scary because we all know what workers do when they are machining. They might have a mask on, and as soon as they finish drilling or whatever they're doing, they pull the mask off. But in fact, you might well still be exposed to the cloud of dust that is floating around, even if it's not visible to the naked eye. So that's one careful thing to remember. When you've got controls in place, they need to stay in place. So this is just really the first phase of this presentation. I'll probably pause here to see if there are any questions related to silica dust as a particle or as a crystalline particle at all. I'll just pause for a second, and Nicole can alert me and read out any questions.
There doesn't look to be any as yet. No.
Okay, good. I might push on then. Now, as we know, the exposure limits are going to be changing in as of 1st of July, as I mentioned in the intro. But before I get to what they change to, I want to give you an idea of the magnitude of the problem that we're looking at. It's pretty scary. If we look at a typical construction application, whether it be grinding concrete where my mouse is hovering, whether we're cutting concrete or masonry where my mouse is hovering again, or heavy drilling or braking, a lot of dust is generated, but I don't think many of us take the time to actually to measure that or think about that in a sort of a kilogram format. So I'll just superimpose the levels of dust that are generated in these operations over these photographs. So when we're looking at concrete grinding, even with a 5-inch grinder, we can liberate up to 3 kilograms of dust per hour. And I think we probably have an intrinsic feel that that's the truth, because when you look at the cleanup operation after grinding, if it's been done without any capture equipment, there's a lot of dust that gets swept up. Diamond cutting with the 9-inch cutter is even more, and this is a really difficult dust situation to control. It can liberate up to 12 kilos of dust per 1 hour period for continuous switch on time. It's a very significant problem. Now let's turn this picture into the concentrations of dust that this can result in. And when I say concentrations of dust in the respirable range, i.e. less than 4 microns. So that's dust that you can breathe right into your lungs. So I just did a literature search over a range of different studies to kind of get an idea of what this can look like, and later on we can compare it to some of our in-house tests. But when we're looking at just concrete grinding, we can look at a dust concentration of 0.83 milligrams per cubic meter over an 8-hour weighted period. It's a very high concentration of respirable dust. The silica dust would be a fraction of that. So your silica dust concentration would be less, but still even this number is way higher than the new working exposure standard of 0.05 milligrams per cubic meter. So this is with no capture in place, just spewing out into the environment. Cutting is even worse. It's at a level of 1.6 milligrams per cubic meter. Again, many, many orders of magnitude higher than our future working exposure standard. So that, I think that kind of puts some boundaries around the challenge that we're looking at within the construction industry. Now, with the exposure standard changing, it's going to require fairly significant change in behavior. When we look at these machining operations relative to the old standard, when you put these operations in place with control measures, and you wear protective equipment like a face mask, which would have a protection factor for a P2 mask of, for example, 10 times. In many of these operations, you'd be in the clear. So, for example, grinding, you could get to a lower concentration than 0.1, braking, a very low concentration, even light drilling. But still, diamond cutting is a major risk factor, and there you would be needing to look at wet cutting, even in the context of the old working exposure standard. So then let's superimpose the new working exposure standard. Really, even with respiratory protective equipment, without controls, you'd be in the red zone for all of them. So this is a kind of situation where we need to look very, very carefully at what engineering controls to attach to these type of operations, and then use in conjunction with protective respiratory equipment, for example, the face masks, that we can finally control this. So we're in a different space completely in the industry. We have no choice really but to widely adopt engineering controls for capturing dust. That's assuming there wasn't a substitute. But the purposes of this discussion, I'm assuming because we're talking about remedial work as opposed to ground up construction where you can do substitution. This is the engineering controls really is the direction in which we need to be heading in. So this is another point at which I can pause for questions regarding the new exposure standard and its impact on how we work in construction, and see if any questions have come up.
Nothing has popped up. Does anybody have anything they want to say verbally? No.
Okay, good.
That's good. You're answering all the questions.
Right. Well, now we'll get into the very interesting stuff, which is what are the engineering controls? And then very importantly, what impact do they have? How effective are they in reducing the overall concentrations to a very low level such that we can safely work within them? I'll run through a few. The typical engineering controls that we can attach to the concrete cutting operations are very simple hoods that can be attached to small grinders, and then the more sophisticated wet and dry, specially designed cutters, electric cutters that have got a shroud that can suck up dust if it's being used dry, or you can attach a continuous stream of water if you're going to be cutting wet. Now, the critical element in the dry cutting operation is the vacuum cleaner. Now, all of the WorkSafe bodies within Australia recommend either an M-class vacuum cleaner or an H-class vacuum cleaner for use in construction. WorkSafe bodies in Queensland and New South Wales, or pull back on that. The WorkCover in Queensland have now got an official practice document for working with artificial stone, and there they specify an H-class vacuum cleaner. But for general construction activities, an M-class vacuum cleaner suffices. Okay, and that's a critical link in this. A well-maintained and fit-for-purpose M-class vacuum cleaner is the thing to be using. The next engineering control is that we can look at is fitting turbo pumps to petrol-powered saws. So instead of just using a gravity flow of water to try and suppress dust, we were able to attach pumps to the tools such that you pump water onto the blade at a very high pressure. And pumping water onto a blade at a higher pressure enables better adherence of the dust particles to the water particles to generate a more effective slurry. So the actual dust concentration isn't as high because you don't capture all the dust with wet cutting, you only capture part of it. Also in the industry, we're starting to see widespread adoption of grinders with purpose-built hoods. And a key part of looking at any particular engineering control for grinding is this interface between the surface of the concrete and the actual hood that surrounds the tool. You need effectively a skirting in place, either with plastic baffles or nylon baffles, and that forms the seal between the concrete surface and the hood itself. If it's just a hood, you still get a lot of dust leakage out from the side. Now, if you are machining rough concrete, which was a question that emerged in the last webinar, clearly you do get some leakage, but still the majority of the dust can be captured in these types of custom-built grinders. On-tool dust extraction for drills is a good method of capturing dust. And then using technology that we're seeing in the industry more and more for large diameter drilling is using products like hollow drill bits. Now, the advantage of using something like a hollow drill bit and the advantage of many of these engineering controls is when you remove dust at the cutting element itself, right at the tip of the drilling head, you reduce friction of the overall machining system because you aren't getting dust transported up the flutes of a drill bit. So the drilling process is actually faster. So not only are you controlling dust whilst you're drilling, but you're also able to drill slightly faster. The other advantage with using this type of system is that when you're drilling holes to inject chemical, be that a sealant or be that a chemical anchor, whatever that sealant might be, you're left with a completely clean hole. So you don't need to flush it or blow it out with compressed air, because equally blowing a hole out with compressed air, you get covered in dust. So that's there are multiple benefits for using this kind of hollow drill technology, and there are quite a few suppliers in the market, including ourselves, who offer this type of technology. Even braking, we can now attach engineering controls to breakers in the forms of hoods. Now, often with braking, it's a very uncontrolled kind of a process, and you still see a lot of dust being generated in this particular application. But the dust that's generated is generally in the coarser range, and the fine, so it gets liberated, and you still see somewhat of a cloud of dust. But the fines, or the respirable range, are still sucked up through these hoods and recovered in a vacuum cleaner. And there you have an advantage in these kind of light demolition or remedial works, where if you've controlled that fine dust during operation, the cleanup effort is less, and the surrounding physical inhabitants' complaints are less, because they're not getting dust drifting into their surrounding office buildings or surrounding public areas and that sort of thing. So you're able to contain the overall dust footprint much closer to the machine and to the operator. Now I'll just run through how effective these controls are. And Nick, is there a question there?
There is. Jonathan McRae from Apex Diagnostic has a question about your vacuum cleaners. What's the differences between the two classes of vacuum cleaner?
And when we say the two classes, the M and the H, I'm assuming? Yeah.
I'm assuming yes.
Yeah. Okay. Well, I'll actually touch on all three types of vacuum cleaners. The one that has been most popular in the industry is the basic L class, which is has a dust efficiency capture of 99% through its filters, and the M class has 99.9, and then the H class has a filter efficiency capture of 99.995. Now, on the face of it, then you'd think, well, why don't I just go for the H class? But the effectiveness of the overall system is a function of the grinding or the cutting element you're using, the effectiveness of the hood, as well as the vacuum cleaner. So in terms of dust capture effectiveness overall, there isn't a huge difference between an M class and an H class. The other potential danger with an H class is really points towards the design intent of an H class. An H class vacuum cleaner is intended for sucking up fines of very hazardous material like asbestos, lead-based paint, and those types of products when it's in very, very low concentration. When you use an H class vacuum cleaner in this kind of compact size, with applications that are generating a huge amount of dust like concrete cutting, concrete grinding, etc., that very, very compact, fine H class filter can get clogged very, very quickly. So unless you're exchanging filters extremely frequently, you actually do a worse job of collecting dust because those filters blow out. So the M class is probably the most fit for purpose machine for construction work when it comes to working with concrete. I hope that answers the question.
I have another one though.
Okay.
Tony Matthews has asked, Has Hilti undertaken any studies on the approximate reduction as a percentage of the dust generated when comparing the use of a vacuum cleaner and not using one?
Yes, yeah. So we've done these studies, but we can't run them for very long because the standard European methodology for running these dust tests is conducted in a 200 cubic meter enclosed space. So you can't put an operator in there for more than a few minutes. So you can't compare the standard 1 hour test head to head with controls versus no controls. So generally we kind of calculate backwards to extrapolate the amount of dust that we recover in the vacuum cleaners after machining, and then we calculate the concentration of dust that would have been in the environment had we not captured it. So roughly speaking, these kind of engineering controls differ slightly from system to system, but roughly speaking, you're able to capture, depending on the application, between 90 and 97% of the overall dust that's emanated.
Right, I have another one
Yeah.
from Brian, and I'll apologise if I mispronounced your surname, but Brian Magdalanic. How often should the M-class filters be cleaned?
It's an excellent question, and I'm so pleased it was asked. And can I ask that we pause on that question, because in my latest slide, I'm actually going to talk about that specifically with regards to exchanging filters. So I will deal with that in a later slide.
Beautiful. Well, that's it for now.
Great. So looking at my stopwatch, I'll just I'll push on with the topic of how effective are some of these engineering controls when measured in standard testing, and just give an indication of just what we've been speaking about actually. So when you attach an engineering control to a big concrete cutter, and we cut continuously in our standard test in our enclosed space. Now the enclosed space has a very significant impact, as you can imagine, on the final outcome of your dust test. When you conduct these kind of tests when you're doing these kind of operations outdoors, just the natural ventilation reduces the dust concentration very, very quickly. But in an enclosed space, cutting continuously for an hour, we get these levels of dust concentration, so up to 0.3 milligrams of dust per cubic meter. So really, in the light of the new workplace exposure standards, the operators of these types of pieces of equipment need to be either switching to wet to reduce that dust load, or be using respiratory protective equipment. When with the P2 mask, that will be dropping to about 0.03 milligrams per cubic meter. So you get to you're working within a safer within a safer zone. When we look at concrete grinding, it's a much easier system to control. Just grinding again in the same standard test in a 200 cubic meter enclosed space with a 6-inch grinder, we got silica concentrations of 0.043 milligram per cubic meter. Now then, if we put a dust mask on in that instance, then you'd reduce the load on the operator down to 0.004. So again, well within that safe area. Now, just a word of caution with this kind of test data. It's very difficult to extrapolate this to, what does an 8-hour working day look like? So one has to see this in the context and interpret in the context of what is the actual switch on time that my operators are experiencing in the workplace? Is it over a full day? Is it 1 hour? Is it 2 hours? Is it 30 minutes? And that gives you a better indication of what the concentration of dust might look like. And then one has to put additional factors into place. Or is it a naturally ventilated area? In which case the dust concentration reduces considerably as well. But using well-designed grinding equipment with PPE is a very simple. Well, it's much simpler than cutting, certainly. Much simpler process to control. Similarly with light drilling, with onboard extraction, here's an example of such a tool, and I think Nick last week showed a few examples as well. Again, the light duty drilling is a very easy application to control, but even without protective equipment, without a mask, you're coming really, really close to the actual working exposure standard. So even with light drilling, it's a pretty good idea, if it's on a continuous basis over a full day, to be wearing a dust mask. Then with the hollow drill bit systems, we are able to stay below the 0.1 kind of mark with this particular test. It was done with a German insurance body called BG Bar, and they don't release the exact data that was achieved within the test, but they just let you know if you've passed a gate or not. And this particular test showed that we passed the gate of being less than 0.1 milligram per cubic meter with a kind of a heavy drilling application. So again, pushing home the point that these types of heavy drilling applications, if they're done on an all-day basis, they really need to be done with respiratory protective equipment. And we saw quite a few examples of those last week as well. So either the half face mask or the full face mask, depending on the user. So now then, yes, this question of the M or the H class vacuum cleaners, what are some of the critical variables that surround the operations, and how often do I need to change filters? Now, it's a strange thing, a vacuum cleaner in a construction environment, because you see a box, and you kind of think it's kind of like a tool, and I'm just gonna use it. I mean, honestly, if we look at ourselves in the mirror, how often do we clean the filters aside from emptying the bag in our household vacuum cleaners? And it's not real often, but it's a critical element. And the state of the filter, regardless of supply of your equipment, the state of the filter of your vacuum cleaner has a very strong bearing on the final dust concentration that you would experience. These filters are made of a woven polymer, and like any woven polymer, they can wear over time. And if you have a very high dust concentration, they can become clogged. They can be washed to extend their lives a bit. In the most instances, we recommend, if you are maintaining them by washing them, they can last up to 6 months, and you certainly need to exchange them at a minimum on a six monthly basis, absolute minimum. Some contractors that we deal with out of experience, when these vacuum cleaners are in use all day, every day, they prefer to visually inspect them, and if the seals are broken in any ways or start to degrade, and if you can see like clear evidence of discoloration of the fins, that's the time to change them as well. So a combination of an absolute maximum of a 6 month period and regular visual inspection to see that they're still in good operating condition, that's really the way to go with them. So regardless of manufacturer, the message is look at these filters very, very quickly. And indeed, when we get vacuum cleaners into our repair center, the vast majority of occasions, they need a repair because their filter has never been replaced, and dust-laden air is just clearly flowing through the vacuum cleaner and damaging the electronics and the motors. So it's an important element to keep a hold of. And also with vacuum cleaners, like a hidden danger is, and this has been backed up by quite a few studies we've seen from principal contractors. A hidden danger with vacuum cleaners is the emptying of them. So the laborer who gets to empty them into a skip, if a bag isn't being used, they just upend them in a skip and they get covered in a cloud of dust, which is not good for the health at all. So you have an option of either to use bags for vacuum cleaners or paper or fabric bags that can be closed off and disposed of in a skip. So, these things, they sound like such minor things, but they're actually a very important element in your overall mission to reduce dust concentrations on site. So you can have on paper all of the elements in place, hoods, the right inserts in the tools, the correct class vacuum cleaners. But if the vacuum cleaners themselves aren't in good working order, you're not going to get the health outcome that you need. You know, and as a supplier, we try and do our bit to work within the whole change management of what is required in within the industry space, to educate people about these sorts of things, which systems can you use, how to maintain your vacuum cleaners. So our people are always ready and willing to do this training within classrooms or on site, because the change management involved in adopting, in moving from, well, you know, a working exposure standard that was pretty easily achievable using normal construction gear to this new working exposure standard. It's not all that easily achievable unless you're working with the correct gear and unless your people have been well trained and are well aware of the risks. So that's all my formal slides, and very happy to take questions at this point.
Are there any more questions?
Not yet. What about robotics, Dr. Sterling? Any current information on demolition robots, things like that?
You know, many of the demolition firms that I see are either currently investing in robotics for demolition, for sure, and now starting to investigate, and we're also investigating robotics in grinding.
Mm-hmm.
You know, much like you see those vacuum cleaners sniffing around, those auto vacuum cleaners, those types of equipment. But one step before then as well is this question of making sure machines have the technology to speak to one another. So, for example, I've just been discussing, and the questions were asked: how do you know when to change the filter in a vacuum cleaner? That's an easily solvable question if you have a vacuum cleaner that can alert you to when its filter is clogged, and that's technology that's under development at the moment. And then, better yet, is a vacuum cleaner that can talk to the tool to tell the tool that it's not working anymore, and therefore stops the tool working. And there's also pieces of technology that are in development. And then, furthermore, for supervisors and for health and safety managers, is being equipped with like ready reckoner devices or instruments that you can walk around on site that can tell you what your dust concentration is in real time. And those are also pieces of equipment that are under development.
Good. Look forward to seeing them. Any other questions?
No, that looks like it.
Okay. Well, thank you, Martin.
Great.
If anybody does happen to have a last minute one, please jump in while I'm doing the outro. Blaine's in a tender meeting, so he's having a group hug, trying to win some more work and stay employed, I guess, which is important these days. Again, I'll just introduce next week's webinar, which is the importance of concrete surface preparation. It's the key to success and preventing avoidable failures. Our speaker for that one would be Mike Rutherford, who's the principal of Conspectus Queensland Proprietary Limited, and they're an independent consulting company who provide specialist asset maintenance, engineering and asset management support services. Mike will be talking about adequate surface preparation being the key to successful concrete repair and also concrete protection projects. Inadequate preparation often leads to failure of the repair or the coating, necessitating further rework. That incurs added expense, operational downtime, and compromised integrity of the remediation and protection works. the maximum there being do it once, do it right, or do it right, do it once. Mike has more than 35 years experience in concrete remediation and protection gained through product development, marketing, contracting and consultancy positions, and currently holds positions with ACRA, Queensland Sub-Branch Committee, and the ACA Applicator Technical Group. Mike's an active ACRA board member as well. He's got individual and corporate memberships with ACRA, ACA, CIA, NACE and SSPC. So for now, again, I'd like to thank Dr. Martin Sterling for putting together this presentation. Appreciate it, Martin. And welcome you all to next week's webinar.
Thank you so much.
Thanks. Thank you.
See you next week. Bye.